Hi everyone. Today we have a question from KTG, Kinetic Theory of Gases. And the scenario today we'll be talking about a rotating column of air, a hollow cylindrical column of air, which is rotating with an angular speed of omega. And we need to find the pressure which is varying with the linear distance. We are provided with the external pressure as P naught and the external temperature as T. Also, we are provided with the density of the gas as rho and the mass of the gas as m naught. So, qualitatively speaking, we are aware of one thing, that as we progress further from the beginning towards the end, the pressure is going to increase, right? Since we are having a greater distance from the center, and the centripetal acceleration will contribute to the increased pressure. So, pressure has to be proportional to some power of x, right? So, talking about the quantitative scenario, we have, talking quantitatively, let us assume an element of width, some dx, at a distance x from the beginning, and let us call the pressure on the left hand side of this element to be P, and pressure at the right hand side to be some P plus dP. So we know that there has to be some increment in the pressure. So we'll have P plus dP as the final pressure on the right part of the element. Now, since the width is dx, we know that the dP has to be dx times rho, which is the density of the air inside of this column, times omega squared x, but derived from the small change in pressure as dy times rho times g. Here the effective gravity is nothing but the centripetal acceleration provided by the angular velocity omega. We don't have g as gravity, we have centripetal acceleration as the only acceleration provided to us, and rho is the density of air, and dy here in our scenario is just the dx. So we know that the pressure is varying this way. So we now, from this equation, we have the value of rho as Pm over RT, and calling this as equation 2, and then just plugging in the value for the density. So the moment we plug in this value, we have a modified equation for 1, and this modified equation for 1 is dP as Pm over RT times omega squared x dx. Now all we need to do is to integrate this, but we won't integrate it. We'll have this P over here in the denominator. Of course, the pressure is going to depend, so we'll have to have this on the LHS for the pressure dependencies. So we have dP as dP over P as m omega squared over RT times x dx. This thing will be integrated, and the limits will be kept from a distance of 0 to, let us say, some r distance, right? So we have this as r as well. This entire thing has been called as r, and the pressure is some P at an x and P naught at the external point, since we were given P naught as the external pressure. Now we'll integrate this from P naught to P. So upon integrating this, we get the natural log of P over P naught, which is to be equal to m omega squared by 2RT times r squared. We just integrated this, and that's where the 2 came from. So we have this, and then we have the pressure as a function of distance r, which is to be given by P naught times e to the power m omega squared r squared by 2rt, which is our final answer. So we have the pressure dependent on the distance for the rotating column of air. So that is it, people, for this one, and thank you for your time.